record. So make sure that we're recording. Okay, we are recording right now. Okay. So this is the overview, as I told you guys, about the F distribution that we used yesterday to do an ANOVA test, which is called analysis of variance test, to check if 3 or more means are equal or not. As I said one more time, the F distribution is a family of curves. Each curve is determined by 2 degrees of freedom. One will call degrees of freedom of numerator and the other one degrees of freedom denominator. We will not use this today because we will not do any critical value. We're using the p-value approach, so you don't have to worry about that. The F distribution is right skewed. It's a positively skewed. It is always positive, as you can see, and the total area under any F distribution curve is equal to 1. Let me go back now to section 10.4 and do a couple more examples on the ANOVA test that we started yesterday. So I'm gonna stop sharing here. I'm gonna share a different screen with you guys. Just 1 second. So I'm gonna open a new screen. So let me just pause the recording for 1 second and get the other screen. Recording. Okay, I'm gonna go backward. I'm gonna start with section 10.4. I got a couple more examples for you guys to do, covering section 10.4. So it's right here. So the one-way analysis of variance for students who were not here yesterday is used to determine whether 3 population means or more are equal or not. So this is a test. If you have more than 2 means, you must use the analysis of variance. In chapter 8, you learned how to compare 2 means, mu1 and mu2, but when you have more than 2 population, you will need to use analysis of variance, which is called ANOVA, to check, to test whether the means are equal or not. The one way ANOVA compares the means between the groups you are interested in and determine whether any of those means are statistically significantly different from each other's. There is one statement, guys, a generic statement. It doesn't change from one problem to another. This is it. Your null hypothesis will be always mu1 equals mu2 equals mu3 equals mu4, whatever, how many means you have. And then HA, please try to remember this, at least one of the means is different from the others. That is the statement that you should put in any ANOVA test. Okay. Assumptions of the test. There are 3 assumptions in order to be able to do the test. The samples must be independent. And the population are normally distributed or approximately normal. So the samples must come from bell-shaped distributions or approximately normal. Doesn't have to be perfectly normal, but approximately normal. And population variances are equal for the 3 sets or 4 or 5. When he asks you to test the claim, that means he's making sure that the assumptions are valid, so you don't have to worry about it. You just run the test. And we will be using what I told you guys. We will be using the F distribution to perform the test. And when we use the calculator, we'll be using the test called ANOVA. And then the ANOVA works the following way. You input the lists into the calculator, and then you hit calculate. It will give you the test statistic F. It will give you the p-value, and this is all what you need in order to perform the test. So these are the requirements of the test. What I'm gonna do right now, guys, I'm just gonna do a couple more examples and show you how that works. So have your calculator handy, please. Okay. Just get the example. 1 second. Here they are. Example 5 and example 6. A medical researcher wishes to try these 3 different techniques to lower cholesterol levels of patients with high cholesterol levels. The subjects are randomly selected and assigned to one of 3 groups. Group 1 is given medication, Group 2 is given exercise program, and Group 3 is given diet. At the end of 6 weeks, each subject's cholesterol level is recorded. Test the hypothesis that there is no difference amongst the means. So we want to test the hypothesis that there is no difference amongst the means. Okay, here's how you begin. We state the null and the alternative hypothesis. mu1 equals mu2 equals mu3. I don't need a mu4 here, guys, because I have only 3 groups. And HA, at least one mean is different from the others. My question to you guys, can you tell me where the claim is? Is it an HO or HA? Test the hypothesis that there is no difference among the means. Okay, my chat box is active. Let's see. I agree. The student says it is an HO, guys. Yes, because no difference means equal. All right, so great. I'm gonna pause the recording, guys, for 1 minute and let you enter the data in L1, L2, and L3. So let's do that. So I put my data, group 1, group 2, group 3, and L1, L2, L3. And now I'm gonna go to stat, calc, tests, scroll up. It's the last test, ANOVA. And enter L1, comma, L2, comma, L3. And close. That's all you have to do, guys. All right, enter. And you get F and the test statistics. So I'm gonna copy them. So ANOVA, this is L1, L2, L3. You understand that you have to input the data in order to be able to use it into the calculator. And then you get the F, which is 11.09. That's a big test statistic, and the p-value is going to be small. When the test statistic is large, the p-value will be very small. And alpha is 0.05, which is less than alpha right here. Reject HO. And the conclusion. There is, let's see if a student can help me, enough evidence at the 0.05 level of significance to what, guys? The claim is in HO and we rejected HO. So what do we say? There is enough evidence to what? To, that's important because that will be the last step that you have to choose to reject the claim. Thank you. To reject the claim that there is no difference among the means. So probably there is a difference. And be honest with you guys, I can see probably the difference. It looks like in group 1, they're different from the other 2 groups if you look at them carefully. All right, next question. Example 6. I will share all those notes with you today, right? Chapter 9 and 10. I'll scan them and email them to you after we're done today, if you need the notes other than the videos. A researcher wishes to determine whether there is a difference in the average age of middle school, high school, and college teachers. Teachers are randomly selected. Their ages are recorded below. Test the hypothesis that there is a difference in the average age of each group. Guys, some students asked me earlier, what's a hint to know that this is ANOVA test? The hint to know that this is ANOVA, when you have 3 columns of data right away, guys, more than 2 columns, you know it's going to be an ANOVA test. So this is going to go to L1, this is going to be L2, L3, and your HO, guys, is not going to be any different from what we put before. And watch, and HA, it's going to be exactly the same as I put in the previous exercise. At least one mean is different from the others. What is the claim here, guys? Is it an HO or HA now? It says test the claim that there is a difference in the average age of each group.
HA.
Yes, I agree. Correct. So it is an HA. That's very important, guys, because your conclusion, you know, just will be worded differently depending on where the claim is. Okay, let's pause for 1 minute and put the data in L1, L2, and L3. So this is my data in L1, L2, L3. So I'm going to go to ANOVA, stat, scroll up. It's the last test, ANOVA. Second and then number 1, comma. Don't forget the comma. It won't work without it. Second and number 2, comma. And second and number 3, close. Enter. Here you go. So one-way ANOVA. We don't do two-way analysis of variance. It's just one way in this book. So 2.516. So ANOVA, I'll write down what I did here. I think you should agree with me that's an easy test to perform using technology. But it was the most difficult test to perform, guys, when we did not use technology in the past to do this one. It was very, very difficult test. It's a lot of work. So p-value is 0.1142. All right, alpha is 0.01. So that's bigger than alpha. Fail to reject HO. Again, guys, just a final reminder, hypothesis testing is about doing one of 2 things. If you are asked a question on the final, what is hypothesis testing is about? It's about whether to reject a null hypothesis or fail to reject a null hypothesis. This is it. So we fail to reject the null hypothesis. And the conclusion, if you have a fail, you have to start with there is not enough evidence at the 0.01 level of significance. 2, test the claim that there is a difference in the average. There is not enough evidence at the 0.0 level of significance to what, guys? The claim is not in HO this time, it's in HA. So what do I use? To support the claim. We cannot support the claim. We only use the word reject when the claim is in HO. To support the claim, and I'll say it verbally, I'm not going to write it, that there is a difference in the average age of each group. Okay, that concludes section 10.4. Section 10.1 now. Goodness of fit test. It's going to be an easy test because I'm going to demo how to do it on using the calculator. So you will see that in a second. This is the 10.1. Okay, let me just pause here for. All right. Let's go to the next page, 528, and show you another example of the goodness of fit test. I'm not sure why the player is going slow today. Okay, another one page. He does show a lot of work in the book, but it's all using the traditional method, the critical value method. What we're going to do today, guys, we're just going to do the p-value method. It's going to be speed up things. I should have used just the actual book. Okay, never mind. This is going very slow. I'll just project my book and show you some more examples. Stop sharing here, and then I just share the Ladybug screen. And let me show you some more interesting examples of goodness of fit tests. There's another example. I've been trying, to get to those. Okay. Ages of moviegoers. Someone make a claim that the distribution of ages for people who go to the movies is listed right here. You want to check if this distribution is still valid or not. So they claim that the people who are age 18 to 24, 21% of people who are aged 18 to 24 go to the movies. 22% are age 2 to 17, 19% are 50 plus, and so on. You want to test this claim, guys. So in order to test this claim, you have to randomly select the people and ask them, what's your age and how often do you go to the movies? And then, or you select, people who go to the movies, stay by the door, main entrance, and ask them, how old are you? And take notes and get some information, and then come back and test the claim, which I'm going to show you how to do that. Here's another example of the goodness of fit test. Distribution of Americans who drink coffee per day. They say somebody is making the claim that 36% of Americans don't drink coffee. 26% drink 1 cup, 19% drink 2 cups, 90% drink 3 cups, and 10% drink 4 or more cups per day. If you suspect that this is not valid, you can check it, guys. Survey people and ask them how many cups of coffee do you drink by day, and get the responses, and use those responses against, just this distribution, and see if the distribution is valid or not. I'll show you another example so this will make more sense to you. Ordering delivery. Someone is making the claim that day of the week Americans are most likely to order food for delivery is distributed as follows. They say 36% of Americans order food for delivery on Friday. It goes down to 24% on Saturday. Then it goes down to 7% on Sunday. Probably if they eat the leftover from Saturday. And so on and so forth. If you want to study this claim, guys, you can survey people and tell them what day of the week do you order food for delivery, and record this information. The information that you collect from people are called the observed information. And the information that you have in the percent are called the expected information. So I'm going to show you now, guys, with an example, and how to do a goodness of fit test, testing a distribution of proportion, whether this distribution remains valid or is not valid anymore. So let's do a couple examples. Have your calculator ready, and let me show you how to perform those tests. All right. So in order to perform the goodness of fit test, we need a new distribution. So you learned about Z, T, you learned about F distribution for ANOVA, and now the last distribution, I promise this is the last one, it's called the chi-square distribution. The chi-square distribution, guys, looks like this. It's a right skewed distribution. It is a positive distribution. It's skewed to the right. The values are always positive. Total area under the curve is always equal to 1, and it uses degrees of freedom. And the degrees of freedom, in this section 10.1 is number of categories minus 1. which you'll learn later how to find this one. Number of categories -1. So total area under the curve is 1. Chi-square curve starts at 0 on the horizontal axis, extends indefinitely. So this tail, guys, doesn't touch, just the x-axis. It goes there indefinitely, but it is very close to the x-axis. It is right skewed, as I told you, okay? And as the degrees of freedom become 30 or more, this curve tends to lean toward becoming a bell-shaped curve. So 30 is the cutoff number when those curves become pretty much like a bell-shaped curve. All right. So the chi-square goodness of fit test requires that you collect 2 pieces of information: observed values and expected values. And I'm going to show you how to find the expected values, because the observed values they will be given to you. For example, look at this example right here. This is a sample of 500 crimes. Someone is making the claim that the distribution of crimes is as follows: 12% are murder, 5% are forcible rape, 55% are robbery, and 28% are aggravated assault. So these are, guys, the frequencies that you need to study or make a claim about. Now here, these will be given to you. These are the observed frequency. How do we get the observed frequency? We go to our records of 500 crimes and see how many of them were murder, how many of them were rape, etc. So we get this information without making any efforts or without doing any calculations. It's all observed values. We don't have to do any work to get them. Now the expected values, if you think that 12% of the cases are murder, so your expected values should be 12% of the total, which is 500. So if I wanna find the expected values of murders, I can do 12% of the grand total, which is 500. That's gonna give me 60. So this is what we expect in theory, and this is what we got for real. You can see that 60 and 56 are close together. So probably this distribution is a good distribution. It's still a valid distribution. 5% is rape. So if you want to figure out the expected number of rapes, you just do 0.05 times 500, which is going to give you 25. Well, you see the actual number of rapes is 26. So that is very close. So that probably will make you lean more and more toward believing that this distribution is valid. But in order to check if it is valid, you cannot just look at it and say, well, it looks good. You have to do a hypothesis test, and that's what we call the goodness of fit test. So I'm going to walk you through a complete example, guys, in testing a goodness of fit test. Let's go there, page 2. In order to do a goodness of fit test, you have to make 2 assumptions. Or expected values must be greater than 1. And at most 20% of the expected values can be less than 5, and the rest of them has to be more than 5. Well, guys, if he asks you to perform a goodness of fit test, you don't have to worry about the assumption, because the assumptions are gonna work. For the steps, 5 steps: state the null and the alternative hypothesis, calculate the test statistic. It is called chi-square here. Find the p-value, and then reject or fail to reject the null hypothesis, and then state your conclusion in words. I provided you guys with summary on how to use StatCrunch and how to use the TI-84 to perform this test, but I'm gonna demonstrate it right now. There you go. This is the first example. A teacher figures that the final grade in the chemistry department are distributed as follows. So he believes the grades in the chemistry department are distributed as 25% of students will get A, 25% will get B, 40% will get C, 5% will get D, and 5% will get F. At the end of a randomly selected semester, the following number of grades were recorded. These are the observed values. So we got the grades from how many students. If we add them, we get 160. That's a total of 160. So out of 160 students taking chemistry, we got the following grades. Test the claim that the grade distribution for the department is different than expected. Before we do that, guys, let me show you how to state the null and the alternative. And it is generic statement. It does not change from one problem to another. HO will be always distribution is as claimed. As claimed above right here. And HA, guys, will be distribution has changed or is not as claimed. Now, what distribution we're talking about here? It's distribution of grades. Okay. Now, where is the claim here? Can someone tell me where the claim falls here? Is it in HO or HA? Can you guys help me with this? Because it says it's different than expected. Exactly. I agree. That is the claim. Step number 2, guys. Have your calculator handy. We have the observed values. I'm gonna list them here. I got 42 for A, 36 students got a B, 60 students got a C, 8 students got a D, and 14 students got an F. Now we need the expected values. For the calculator, it needs the expected values. They call them E. Now observed values are called O. Okay. Can students help me find the expected values? If this distribution that the teacher claims is valid, how many students would you have expected to get an A? How would I figure this out? Remember, the total is 160, guys. What do I, exactly, 25% of 160. It is a percent of the total, guys, which is 40. The second one, 25% for B, as you can see, guys. It's 40. The next one, it says 40%. So 0.40 times 160 is 64. Oh, wow, they look close, guys. Look, 42, 36 to 40, not a big difference, not a big difference. So we're good so far. Maybe the distribution is good. D, we got 5%, 0.05 times 160. Oh, perfectly, 8 here. Perfect match. And here, 0.05 times 160, which is 8. If you guys add the O's or add the E's, you should get 160. Here the sum is 160, and here the sum is also 160. If you don't get 160 here, you've made a mistake somewhere. Okay, you're ready for the calculator? Get your calculator ready. I'm gonna go to the calculator test, and we're gonna show you how easy this test is when you use technology. Just as long as you know how to interpret, that's good enough. So you go stat, edit. Oops. Stat, edit. You need to enter the observed values and the expected values into the calculator. So you just go to L1, clear it, and enter the observed values, which are 42, 36, 60, 8, and then 14. Then, guys, you go to L2. I'm gonna clear it and enter the expected values, which let me show you what the expected values are. I got 40, 40, then I got 40, then I got 64, then I got 8, and then 8. All right. Let me clear L3 if it is a bothersome here. I'll clear it so you don't need to be bothered with this. Okay, this is L1 are the observed values, L2 the expected values. Now you go to stat, tests, scroll up, and you guys, you can see the hint. We're doing goodness of fit test. There's an abbreviation for it. It says GOF test, chi-square goodness of fit test. It's letter D. All right. It's asking you, where did you put your observed? I put him in L1. Where did you put your expected values? I put him in L2. My degrees of freedom, now I need to change this. Your degrees of freedom, if number of categories in your distribution -1. I have 5 categories, A, B, C, D, F, 5. If you -1, it will be 4. And hit calculate. Here's the test statistic. It's called chi-square and the p-value. So I write down what I did. So we went to, so we put this in L1. We put that in L2. Then we went to stat. And then we went to chi-square GOF test. Observed, we're in L1. Expected values, we're in L2. Degrees of freedom. So if you review this later, its number of categories -1, which is 5 -1, which was 4. We got chi-square, which is 5.25, and p-value, guys, let me write it down, 0.2626, which is more than alpha. So you failed to reject HO. And you say there is not enough evidence at the 0.01 level of significance to support the claim. That the distribution of grades has changed. It didn't change, guys, because you notice the observed values almost match with the expected values. If there is a match, if there is no big difference between the observed values and the expected values, that means the original distribution is still valid. All right, so this is the first example. I'm gonna go ahead and do another example. But before I do that, if you have any questions, please feel free to ask. All right, let's go to the next one. Have your calculator ready for the next question, guys. Here you go. A doctor believes that the proportion of births in this country on each day of the week are equal, uniform. A simple random sample of 700 births from a recent year is selected, and the results are below. At alpha equal a significance level of 0.01, is there enough evidence to support the doctor's claim? So the doctor claims that the number of births on any day of the week, they're pretty much the same. So if there were like 100 on Monday, 100 new birth will happen on Tuesday, 100 on Wednesday. That's what he claims. So in order to study the claim, we went to the records, we collected 700 births at random, and we checked. This birth was born, this baby was born on which day, and we got the information and we have the table. So these are called the observed values that you get from the record, and when you survey people, these are the observed values. And these should go to L1 always, guys. All right, so let's do this one. So HO, distribution is as claimed. Distribution of births is as claimed by the doctor. And HA, distribution of births, is not as claimed. Or you can say has changed. What is your claim, guys, here? Is it in the null or the alternative? Can you guys tell me, please? It says a doctor believes that, okay, let me see here. And the null, correct. And I like you to change this here, guys. That shouldn't be a support. When the claim is in HO, you ask if you can reject the claim. So that was a mistake from my side here. Or actually probably the book side, because I copy and pasted this. I won't ask you guys to if you can support or not support the claim if it is not in HA. If it is in HO, we usually ask you, can you reject the claim? So you know right away that the claim is in HO. Okay, I got the observed values, guys, right here. So I got Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. And we got 65, we got 103, we got 114, we got 116, we got 115, we got 112. Do they look that they are the same, guys, for all days of the week, or do you think they are different? What do you notice from the observed values? It seems like, you know, there is less births on the weekend. That's what I see. Okay, these are the observed values. Who can tell me how to find the expected values? He didn't give you percents just like the previous problem, but he says the distribution of birth are equal or uniform. And that's why I put this question there, because I wanted to understand what uniform means. What does he mean by that? Anyone knows? He did give us the percents, but not directly. When he says the distribution, the proportion of births are equal. So what does that mean? So again, the expected value will be, because they are uniform, they are equal, you take the grand total and divide it by the number of categories. 700 divided by 7 is 100. And then it has to be 100 for this, because he says they are equal. And if you guys, if you add those, you're going to get the 700. And if you add the expected values, you're going to get the 700 as well. If you don't get a match, that means something has gone wrong. You're going to get a match here because this is something you don't touch. It's done for you. But for this, guys, you better make sure that you get the 700 here. In an uniform situation, to find the expected value for each category, you just take the total and divide it by the number of categories. So we'll go to chi-square goodness of fit test. We put the observed in L1. I would stick to that, guys, always L1 and L2, expected in L2, and then run the test. So let's make sure, guys, that you enter the stuff in L1 and L2. And run the test. Stat, tests, scroll up. There's a goodness of fit test. My observed are in L1, my expected in L2. And can a student tell me what the degrees of freedom is here? You need to change it. Don't leave it by default. That's from a previous problem. Yes, Julia, you are correct. 7 minus 1, 6. And the reason why she said 6, because you have 7 categories, minus 1 is 6. Calculate. You can do a draw as well, but you have to turn the stat plot off if you want to do a draw. I can show you a draw here. Okay. Okay, calculate, draw. You see how skewed it is to the right, as I told you? Okay, you get chi-square is 26.8. And the p-value, guys, it says 2e minus 4, which is 0.0002. So it is a small p-value. Did you guys get the same thing as I did here? You should, unless if I made a mistake with the input. And if you want to do calculate, you should get the same results. So observed in L1, expected in L2, degrees of freedom of 6. If you hit calculate, guys, there you go. chi-square is 26.8, and the p-value, if it would be 0.00015. If you round it, will be 0.002. Less than alpha. Reject HO. And conclusion. We reject HO, and the claim happened to be in HO, so we reject the claim. There is enough evidence at the 1%. You can put 0.01 level of significance to reject the doctor's claim. So we end up rejecting the claim. Do you guys know what days of the week caused us to reject the claim? It's my weekend, because it's different from the other days. It seems like the other days, Monday through Friday, are very much the same. Look, they're all in 100 or 110. But Saturday and Sunday, they were very different. That's why we cannot say that the distribution is uniform. When I say uniform, guys, that means all percents are the same. You just take 100% and divide it by the number of categories to figure out the percentage. So this will close the discussion of section 10.1, and I'm going to go to section 10.2, and that would be it. So we are doing example 3 about the test of independence, regular exercise, and low, moderate, and high blood pressure are independent. And HA will be regular exercise and low, moderate, and high blood pressure are dependent. And before I continue further, I noticed that my recording was paused here. So I'm just gonna, for the sake, if you guys wanna go back and review the videos, just repeat what I said about this test. So the test for independence, again, it is a test to check whether two variables are related or not related. They are dependent or independent. The two variables will be given in a format of a table they called contingency table. It has rows and columns. For example, I told you about an example to test the claim that a person burger preference place is independent of the person's gender, male or female. So does it really make a difference if the person is male or female when deciding to go to which place to eat the hamburger? That is a question of two variables, whether they are dependent or independent. You cannot say it is this or that. You just have to study this claim. The test of independence is a chi-square test, so it does use the chi-square distribution, guys, that we used in section 10.1. To perform the test, you have to meet two conditions. All the expected values must be greater than 1, and no more than 20% of the expected values can be less than 5. To perform the test, you have to state the null and the alternative hypothesis. The null hypothesis, guys, will always be this: the variables are independent. And the alternative hypothesis will always be that the variables are dependent or related, if you like. Then in step number 2, I'm going to show you how to find the test statistic. And then which is a chi-square, the test statistic. Step number 3, we're going to find the p-value. And if your p-value is less than alpha, you reject the null hypothesis. And then finally, you write the conclusion in the context of the claim. Static Crunch, I gave you information on how to use Static Crunch to perform this test. And I also put the details on how to use the calculator, but we're gonna perform the details on using the calculator right now. So we have this example about a medical researcher is interested in seeing if there is a relationship between whether people, if they exercise regularly, that will affect their low, moderate, and high blood pressure. We got the data in a contingency table. A contingency table, guys, is a table that has rows and columns. This is what we call contingency table. Test the claim that regular exercise and low, moderate, and high blood pressure are independent. The reason why I put independent in HO, because that's the definition of HO. It's for independent variables. HA is for dependent variables. And I think, guys, you should agree with me that the claim is right here, because that's what he says. The next step is to find the test statistic. Okay, to find the test statistic, we need observed values and we need expected values. But the good news is the calculator can find the expected values on its own when you provide the observed values. So we're only gonna feed in the observed values into the calculator. And these are the observed values, guys. This is what you observed. But you must enter those values as they show in the table. You cannot put them in L1 and L2. Then the calculator wouldn't know that you have a table. So I'm gonna show you how to input this data into a table using your TI-84. And this table is called matrix here. So you're gonna learn how to use matrices. A matrix is an array, consists of rows and columns. So it's an array of values. You state them in rows and columns. So have your calculator handy, and I wanna show you how to input those values into the calculator. Ready? So we're gonna go turn the calculator on. I'm gonna clear this and watch, guys. That's gonna be like magic when you be able, you know, just to put those into a table so the calculator can process them. Press the second key and go to matrix, it's right here. So watch me doing the math. Go to edit, enter. So from names, you bypass math, you go to edit, enter. So I'm gonna press enter, guys, watch, right here. And now choose the number of rows and the number of columns. Let's look at this table, guys. It has 2 rows of data and 3 columns. You don't count this as a row that doesn't have data in it, and you don't count this as a column, it doesn't have data. So it's this and that, 2 by 3. So you put 2 by 3, watch, 2. If you don't see a 2 by 3 on your side, just enter 2 by 3 and then enter the values. Here you go. Let's enter the values. 35, 62, 25, 21, 65, and then 28. Okay. I'll pause for a second to let you do this. And after you do that, guys, you can quit. So second and quit. Now I go to stat, tests, and here is your test for section 10.2, guys. Scroll up. It is chi-square test. If I were the one who programmed this, I put chi-square test and put independence test there, but he didn't. But you can see this one, it says GOF, goodness of fit test. So that's for section 10.1. So right here, enter. Okay, did we put the observed values in matrix A? We did. Don't worry about the expected. They're gonna go by themselves automatically to B. And just hit calculate. So you don't do actually anything, guys, just hit calculate. And here you go, that's a chi-square test and that's a p-value. So chi-square test, let me just put what we did. Observed values, matrix A, expected values, matrix B, and then calculate. So chi-square is 3.473, and the p-value, guys, is 0.1761. Okay, that's all I need from the calculator. And now I can process this information. I think you agree with me that the p-value is more than alpha. So fail to reject HO. And what's the conclusion, guys? Test the claim that regular exercise, low, moderate, and high blood pressure are independent. There is not enough evidence at the 0.01 level of significance to what? Can a student tell me? The claim is in HO and we could not reject HO. So what do I say? There is not enough evidence to do what? You guys agree that to reject the claim? Yes, Julia, I agree. To reject the medical. So probably this is going to take you by surprise. How could the walk-in and low, moderate, high blood pressure be independent of each other? Well, probably the age, if you're over 50, it doesn't make a lot of difference, you know, in changing the blood pressure. I don't know, but we could not say that they are related. I was assuming they are related, but according to this test, we're saying that we cannot reject the claim that they are independent. Okay, so this is one question. Now the second one, you might be, guys, in the homework be asked to find the expected values. So let me show you how to find the expected values without making any efforts, you know, to use a formula to find the expected values. So here's how we find the expected values. They're already done for you. Watch. Click on second. Right now, please just have your calculator handy with me, and then click on X inverse, which is matrix. And watch this, guys. Your expected values are already in B. Look, it was changed to 2 by 3 now, just like A. So just go to B and press enter twice and enter one more time. Here are the expected values, guys. See, scroll to the right, you see 28.9, 65.6, and there is one more, 27.3. And then these are, if you don't want too many decimal places, look what you can do, guys. You can go to mode, float. Let's say you want 2 decimal places only, but change it back to float after I'm done. And look, second and quit. Go to second and matrix one more time. Oh, oops, I'm not there. Second and matrix, where is it? Right here. Go to B, and watch what's gonna happen now. You're gonna get only 2 decimals. It's gonna be nice. See? But don't forget to change it back to float. So go to mode and just change it back to float. Just a warning, guys. Sometimes by mistake, students put 0. You know what 0 means? It's gonna round everything to the nearest whole number. So don't do that. Just keep it on float to be on the safe side. All right, the next one, we have one more for this section. Let's see, we got one more. So this is a page 6, it should be page 7. Yeah, right here. A food services manager for a baseball park wants to know if there is a relationship between gender and the preferred condiment on a hot dog. So he wants to know whether it makes a difference if you are male and female. What would you put on your hot dog? Ketchup, mustard, or relish. Test the hypothesis with a significance level of 10%. Okay. So step one, HO and HA, they are the same as the previous problem. So here, variables are independent, but I know what the variables are here. Gender and preferred condiment are independent. Gender and preferred condiments are dependent. Or you can put variables are independent, variables are dependent. If the book says variables, just use variables, the two variables. Okay, guys. Can you tell me this table? How many rows does it have of data and how many columns? Before I continue, because we need to know this before we go to the matrix. So I'm waiting for one feedback from a student or a couple if you can. How many rows and how many columns are there? What is this? No, not 4 by 3. Actual data. Another suggestion, guys. 2 by 3. I agree. It is 2 by 3. Watch. This is totals, guys. We created this one. And this is a total. We created that one. We just add up, you know, just the rows and that doesn't count. What count, guys, is this. It is 2 rows and 3 columns. So yes, matrix 2 by 3. Now you're wondering why he gave you the grand total. I'm going to tell you in a second after I finish doing this problem. So guys, your first step, go to matrix A and input observed values. Okay, let's do this together. So go to second, matrix, edit, to go to edit, enter. It's already 2 by 3, so we're good here. If you want to put a 3 here, we'll put a 3 and then enter. Just enter the values, guys. So you have 15, 23, 10, 25, 19, and 8. That's all. I can quit now. Clear. Go to stat, tests, scroll up, and it is a chi-square test. Enter. You can see it says, are your observed values in A? Yes. Automatically, the calculator is going to put the expected values in B and then hit calculate. Or you can do a draw if you want. Watch. Okay. So the test statistic is 2.948 and the p-value is 0.229. So tests, chi-square test, observed. I'll write them down so you know it's in matrix A, and calculate. So you get chi-square is 2.948 and then the p-value, guys, is 0.229. It's a huge, which is more than alpha. Fail to reject HO. And the conclusion in words for a reader. We didn't stay where the claim is. Test the claim wants to know if there is a relationship. So if they are related, so the claim happened to be here, guys, in HA, because it says test the claim that there is a relationship. Independent means they're not related, no association between them. Relationship means they are dependent, so the claim is there. We failed to reject HO, and the claim is in HA. If you still remember my yellow sheet, guys, we say there is not enough evidence to support the claim. At the 0.10 level of significance, to support the food services manager claim. Cannot support the claim. All right. So this is the independence test. Now, guys, I want to show you the expected values. Let me show you the expected values. And I'll show you in a second why those totals were given to you. So if you were to see the expected values, go to second and matrix, go to B and press enter. And then enter again. It's going to display all the values in B. So you have 6 observed values, you should have 6 expected values. You have observed values 15 here. The expected value of 15 is 19.2. Let me tell you what the calculator did to find this expected value. This is why we put the grand totals here. Okay. This is how it works. This is how you find the expected value. But you don't have to worry about it. It's a calculator can do it for you. To find the observed value of 15, here's what you do, guys. 15 belongs to row 1 and column 1. So you check what is the total in row 1. It's 48. So I'm going to just do this on the side here. Expected value of 15. So in row 1, the total is 48. So you put 48 times. In column 1, the total is 40. So you put 40. And then divide by the grand total, which is what? 100. Can you guys do this for me and tell me what you come up with? You should come up with exactly this. Otherwise, I'm in trouble here. Should be 19.2. Let's see. 48 times 40 divided by 100. There you go, guys. 19.2. That's how you find the expected value. So for 23, if you are to find the expected value of 23, figure out where it belongs to, which row and which column. It belongs to row 1 and column 2. The total of row 1 is 48. The total of column 2 is 42. So you do 42 times 48 and then divided by the grand total and so on and so forth. But the calculator can do all of this in one shot and give you all those expected values. So this is it for section 10.2. Let me see how much time. So we're almost out of time. So I'm going to stop the recording right here and make some few announcements.